Welcome everyone to our second blog post. We're honored to have Dr. Mohammed Alizadeh here today with Cesar and I. And today we're going to talk about spine leaf data center performance. So over the last couple of years, Mohammed has been working, he has a PhD from Stanford, and he's been part of our CTO office for the NCME business unit. He's been working on congestion control within the data center. So today we're going to go through some of his findings, and then we're going to go through some interaction on how this affects the data center going forward. So with that, Mohammed.
Thanks a lot, Chad. Hey, it's great to be here. So I want to talk today a little bit about some of the work that we've recently been doing on characterizing the performance of leaf spine data center fabrics. And just to set the context for this conversation, I want to begin with basically just a simple observation that today's data center networks are really interconnects for distributed compute workloads. What I mean by this is if you look at common data center applications, whether it's, say, a large-scale web service, something like big data, analytics, or high-performance computing, they're all distributed applications. They all have lots of different components, and they're spread across the servers in the data center, and these components extensively need to communicate with each other in order to make these applications work. And because of this, the performance of these applications is largely dictated by the performance of the data center network, and specifically by the time that it takes for the different application components to communicate with messages with each other over the network. And because of this, data center networks need to really provide very high throughput, very low latency connectivity among the servers. And this has spurred a shift in data center architectures over the past several years. And we're seeing sort of a new trend where the traditional Tor aggregation core architectures of enterprise networks are being replaced with new sort of modern data center architectures. And perhaps the most important new architecture that's being widely deployed in the industry is the so-called leaf spine data center fabric design. And the leaf spine design is pretty simple. Basically, you have sort of a tier of leaf switches. Typically, these will be at the top of the rack. And you have a tier of spine switches. And the topology is just this sort of full bipartite graph between the leaf and spine switches, like in this picture. So the leaf spine architecture has a number of sort of very desirable properties. One is that any leaf switch can communicate with any other leaf switch by spreading traffic over multiple paths through the different spine switches. So we can essentially scale the bandwidth of this network by just adding horizontally more spine switches. And this way we can build networks with very little oversubscription, or even if we want, essentially zero oversubscription very easily. The other is that every pair of leaf switches is always exactly 2 hops away from each other. So this network design gives us very uniform and low consistent latency between all pairs of fabric ports. In essence, if you think of what the leaf spine fabric is trying to do, is it's really trying to approximate an ideal switch, what's called sort of an ideal output queued switch. So this is a switch where anytime you get a packet on an ingress port, it will immediately land at its designated egress port and then get queued there potentially until it can be delivered to its final destination. So the leaf spine is trying to approximate this ideal switch, and really our goal in this little study that we did here was to try to understand how close is really the leaf spine fabric to an ideal output queued switch. And importantly, what are the factors, what are sort of the key factors that impact its performance, especially focusing on those factors that the network architect has easy control on. Things like the choice of link speeds, or the buffering at the different tiers of the leaf spine fabric, or things like oversubscription. So the way we conducted this study was we decided to focus on only widely deployed mechanisms. Standard TCP, Reno, and SAC for the transport, which is widely deployed. Standard drop-tail buffering, sort of shared memory and drop-tail queuing in the switches. And standard equal cost multipathing or so-called hash-based sort of randomized load balancing in the fabric. And we looked at several realistic data center workloads that are sort of inspired by measurements that have been done in actual production data centers. So these workloads have sort of a mix of sort of foreground query traffic, which, as I'll describe a little bit later, has so-called sort of incast traffic profile, as well as sort of all-to-all communication between the servers of sort of random dynamic traffic, which has realistic flow size distributions. And again, these have been done based on measurements in real data centers. In particular, we looked at papers that looked at a production data center supporting a web search application, as well as another data center that was supporting a data mining application. And to simulate these workloads, we use the Omnet simulator, which is a packet level simulator. So we basically built this very detailed model of sort of a leaf spine data center fabric with about 100 10 gigabit per second servers. And another important thing about our simulator is that we were able to port the actual Linux 2.6.26 TCP stack to this simulator. So we run the real TCP code for simulating TCP. And this is really important because the big challenge of actually doing a realistic simulation of these networks, a lot of it rests in trying to model TCP and all the intricacies of TCP. So here we do a really good job of this because we use the real code. And just one last thing about the simulation is that the key metric that we decided to focus on was the application level flow completion times. So instead of looking at sort of networking metrics like, say, throughput or latency or packet drops, we looked at the true time that it takes an application to actually transmit a message over this network, and this is really what the application at the end cares about. So we studied a few different factors, and let me just start with the impact of the fabric link speed. So what we were interested in understanding is how do different choices for the link speeds in the fabric actually impact performance? And we considered 3 different designs, and we compared them. So all these designs, this is showing the choice of leaf switch. So you can see that in all cases, the leaf switches have 20 10 gigabit per second downlinks, but the uplink link speeds are different. In one case, we consider 10 gigabit per second uplinks. So we have 20 10 gigabit per second uplinks, or 5 40 gig uplinks, or 200 gig uplinks. So all of these have the same bisection bandwidth. We're only changing the link speed. And what we're going to see here is a simulation where we sweep the load of the network, sort of the average load of the network, and we look at the average flow completion times. And in this chart, I'm going to look at the average flow completion time for the large flows, so things that are above 10 megabytes. And the performance is similar for all the flows, but the large flows allow us to show sort of the distinctions more clearly, so I'm just going to kind of zoom in on those. So this is the performance that you achieve with an ideal output-queued switch. So again, this is kind of like this is not an actual leaf spine design. This is just taking the ideal that we want. And this is what we get when we build a non-oversubscribed fabric with 10 gigabit per second uplink. So you can see that there's a gap to the ideal. But when we look at the 40 gig fabric speeds, fabric links, we see that it's actually very close to the output queued switch. And the same can be said about 100 gigabit per second fabric links. So what we observe in this is that with 40 or 100 gigabit per second fabric links and 10 gigabit per second access links for the servers, we're achieving about the same performance in a leaf spine fabric as an ideal output queued switch. Whereas when the leaf spine fabric links were running at 10 gig, there was a degradation in the flow completion times, and it was as much as 40% compared to the ideal output queued switch. So let me try to kind of give you the basic intuition for why this occurs, and it really has to do with the efficiency of randomized or equal cost multipath load balancing. So Let me just kind of sort of simplify this and consider a basic thought experiment. So assume you have 11 10 gigabit per second flows, and in two scenarios, you need to distribute them across the uplinks of these leaf switches. So again, one of the leaf switches has 20 10 gig uplinks, and the other has 200 gig uplinks. And what ECMP load balancing is going to do is it's going to take every flow and it's going to randomly assign it to one of the uplinks. So this is kind of like a probabilistic phenomenon as to how many flows get assigned to each uplink, and it can be modeled in what's called the balls and bins model. So the idea is pretty simple. So in one case, you have 20 bins, and each of them can fit one ball. This corresponds to the 10 gigabit per second uplinks. And in the other case, you have two bins, and each can fit 10 balls. And this corresponds to the 100 gig uplinks. And what we're basically doing is we're kind of spraying these 11 balls randomly across these bins. So when we do this in the top case, it's actually very unlikely that all the balls will land in distinct bins. If you kind of do a simple calculation, you see that the probability of that happening is only 3.27%. So it's only with 3.27% chance that we'll get 100% throughput. In what actually happens is it's actually quite likely that sort of you'll have two balls at least that land in the same bin. That's basically like a hash collision that happens, and you lose throughput. Whereas if you do this in the other case, the only way that you can lose throughput is if all 11 balls land in the same bin. Anything other than that, the bins will be able to fit the balls. And the chance of basically getting 100% throughput in this case is very high. It's like 99.95%. And so this shows you that, sort of gives you some intuition about why, as we increase the fabric link speed relative to the axis link speed, we can improve the efficiency of ECMP load balancing. So the next thing that we wanted to look at was the impact of buffering. And we really wanted to understand, where do queues actually build up in a leaf spine fabric? So to understand this, we simulated a topology like this one, which is a 2.5 to 1 oversubscribed fabric. And we basically set the buffer sizes to be very large. So imagine these buffers at the switches are infinite in size, so we're never going to drop any packets. And then we run a workload, and we see, where do the buffers naturally build up, and how much do they build up at the different points of the fabric. So the workload here is a workload that on average generates about a 60% load on those fabric links. And of course, because of the oversubscription at the leaf layer, it's going to have a smaller load at the edge of the network. So to start with the front panel ports, so these are the ports attached to the servers, this is the distribution of the buffer occupancy across all of these ports. So the way to read this chart is that the maximum buffer size that we saw over the course of the simulation was around 4 megabytes in any one of these queues. And if you look at, say, the point of like 0.95 on the y-axis, it tells you that 95% of the time the buffer occupancy was less than a megabyte. If we now look at the leaf fabric uplinks, this is the distribution that we get. Of course, it's larger, and this is because of that oversubscription. The load is higher on the fabric links than at the axis links. And if we look at the spine ports, this is the occupancy that we get. So the interesting thing here is that the occupancy is very similar for the leaf uplinks and the spine downlinks. And this is a phenomenon we see generally in these types of simulations. So the leaf fabric port queues have sort of the same distribution, the same characteristic as the spine port queues. And if you think about it, this actually makes a lot of sense. There's really a one-to-one correspondence between leaf uplinks and spine downlinks. They always run, by definition, at the same speed. And because all the traffic that goes up some uplink comes down another downlink in the spine, these links, these ports also run at about the same amount of sort of traffic intensity and load. And that's why you see this similar distribution. So the takeaway from the previous experiment was that the leaf uplink queues and the spine downlink queues are more or less the same. But we now want to understand, sort of relative to each other, is there any benefit with having a larger buffer in one tier versus another? And specifically, we're going to look at these so-called sort of incast patterns, which have been shown to be especially problematic in data centers. And it's basically this pattern where you get a lot of bursty arrivals of traffic from lots of destinations to a single receiver simultaneously, and they cause buffer overflows. So for the queries which had this incast pattern, we're going to look at sort of 4 combinations of either very small 2 megabyte buffers or very large 10 megabyte buffers at the different tiers of the network. So when we have very large buffers at both the leaf and in the spine, this is the query completion time that we get at different levels of load. Whereas if we had very small buffers at both, this is the performance that we get. So you can see that there's a pretty notable gap with these 2 meg buffers. Now, interestingly, if we leave the leaf buffers to be at 2 meg and increase the spine buffers to 100 meg, we don't get much benefit compared to 2 meg at both the leaf and in the spine. So we didn't really win that much by just adding buffer to the spine. Whereas if we do things the other way, if we have a small buffer in the spine and a large buffer at the leaf, we're actually doing much better. So the takeaway here is that the larger buffers are better at the leaf switches than in the spine switches. And one thing I want to sort of emphasize about this is that the experiment was considering sort of extremes. The 2 meg and 100 meg numbers were chosen to because they can illustrate the point most clearly. But for sure, sort of a 2 meg buffer is definitely way too small. So we're not going to, and I'm not saying like 2 meg is the right number here. It's just to make this point. And this notion of why at the leaf larger buffers are more helpful is really because of the nature of this incast pattern. So an incast, again, is many senders sending to one receiver. The traffic from these senders gets spread across multiple paths as it gets load balanced across the spines, but when it goes to the receiver, there's really a single point of convergence. And so because of this, the traffic is much more bursty at that point of convergence, and the incast is most severe at the leaf. So just to sort of summarize this, our study had sort of 3 main findings. And first was that with 10 gigabit per second access links, when you have a speed up in the fabric links, either 40 or 100 gig, and we didn't find much difference between 40 and 100 gig in our simulation, and you have sort of just standard ECMP load balancing, you get performance that's about the same as an output queued switch. But when the access links and the fabric links run at the same speed, we see some degradation in performance. The second is that the distribution of the occupancies of the buffers are about the same at the leaf and spine tiers. So the buffer sizes correspondingly need to be relatively consistent. It doesn't make sense to have sort of very like small buffers at one tier and massive buffers at a different tier, because essentially the bottleneck will be at the tier with the small buffers, and you won't be able to even use the buffers at the that are much more orders of magnitude more massive. And finally, even though these should be consistent relative to each other, larger buffers, if we are to add buffer, it's more useful to add it to the leaf tier than in the spine tier, particularly in dealing with these incast patterns. So that was kind of the highlights, and you can find all the details about these experiments in the paper that we wrote about this work and was presented at the Hot Interconnects conference in 2013.
Now, quick question about the buffers, Mohammed. When we talk about buffers, large buffers versus small buffers, how is the application gets affected when you compare big buffers versus small buffers in a network, as today's network, where you have multiple different type of applications? Mm-hmm. How does the TCP, UDP affects the application?
So the way to think about it, so the main purpose of buffering is to absorb sort of transient oversubscriptions of the network links. When you have more coming into a link than it can drain. But the key word there is really transient. If I have a sustained oversubscription of a link, once it's saturated, I'm not going to sort of win any performance by just buffering more and more packets. Once a link is utilized, there's nothing more that I could do. And I might as well keep those packets at the edge of the network and have those flows sort of slow down to accommodate the link draining. In fact, if I just keep buffering sort of more packets at the switch, all I'm doing is really adding latency to my network. I'm not getting more throughput. I'm buffering, and that causes a lot of queuing delay and latency. Now, things like sort of congestion control algorithms like TCP, they've been designed to exactly solve this problem. There's an indication of congestion that happens at the switch. Typically, that's a packet getting dropped, but it could also be some explicit signal like an ECN mark. And that indication is supposed to let the source know to slow down because the link is now fully utilized. But when we add essentially infinite amounts of buffer, we're removing the possibility of giving that indication. So we're essentially disabling sort of the way TCP is supposed to work. So beyond a certain point, once you have a link utilized, there's no reason to buffer more packets. You'd rather have the sources actually slow down.
So you want to make sure that the application is reading correctly in order to handle those type of congestions.
That's right. So yeah. So and this is actually the way TCP is supposed to work. So at a certain point, once a fabric link gets saturated, TCP is supposed to slow down, and the incoming rate into that port is supposed to match the outgoing rate. So you can achieve 100% throughput without buffering sort of virtually infinite amounts of packets. Because if you keep buffering packets, you're just adding latency. In fact, if you think of a data center fabric, this is especially pronounced in a data center. Because in a data center, your sort of natural network latency is very small. You can get a packet from a port to another port and leave spine fabric in 5 to 10 microseconds. But if you keep buffering packets, you add orders of magnitude more latency. So we've seen cases where you take a data center which has a 5 microsecond network latency, and with buffering you can have it be tens of milliseconds or even hundreds of milliseconds. So it can be orders of magnitude more than what the natural latency is. And effectively you lose that very low latency data center fabric property that you were trying to build.
So Mohammed, in a lot of the ACI presentations, we talk about the 30% better flow completion time. That has a lot to do with what you were talking about, if I'm not mistaken. How are we doing that with ACI?
So that's sort of a different thing. So as I kind of mentioned, in this study, our goal was to really look at mechanisms that are widely used standard across the industry, just standard load balancing with equal cost multipathing, standard drop tail buffering, etc. When we were designing ACI, there's a lot of new innovations that we brought to improve the performance of the data center fabric. We have a new way of doing load balancing that is dynamic, and it's significantly better than ECMP. And we have sort of ways of automatically prioritizing latency-sensitive traffic through the data center fabric. But that really requires sort of a deeper dive discussion at a certain point to kind of walk through what we did there. But this stuff is sort of what you'll see throughout the industry. And of course, the ACI can also run in ECMP and standard mode as well. But if I can say sort of one more thing, this study sort of did influence some of the decisions that we ended up making in designing the Nexus 9K platform in sort of both standalone as well as ACI.
Right.
And if I can just say a few words about this. So what we ended up doing is, as you saw, we kind of recognized that it's useful to have some additional buffering at the leaf tier of these networks. So what we did is we basically augmented the buffer that's available with a merchant silicon solution with a sort of a Trident 2-chip with a custom ASIC. And we take sort of a Trident which has about 12 megabytes of buffer, and we add a custom ASIC that adds another 40 megabytes of buffer to that leaf solution. We end up with 52 megabytes of dynamic buffer at the leaf. The other thing was we kind of avoided any unnecessary off-chip buffer, particularly in the spine, because as you saw, the buffer needs to be pretty consistent across the leaf and spine tiers. And by avoiding any off-chip buffer, we avoid sort of the potential performance bottlenecks that come with going to off-chip memory, and as well as we reduce the number of components in our line cards, which significantly increases the reliability. So, compared to a design with off-chip memory, our spine design, our line cards have 2.5 to 3x higher MTBF because of the fewer components. So essentially, we decided to sort of use a consistent ASIC family across all the tiers of the leaf spine fabric. And we really have a design that's optimized for performance, MTBF, power, and cost because of it.
So this is very good because you bring up very good points such as MTBF, power, and cost. So, by not having the off-chip memory, we actually designed it with a merchant, what we call a merchant plus strategy that we had that you guys chose to. And that's what we kind of given the more buffering at the leaf because that's where the incast is coming in.
Yeah.
So,
absolutely.
So this is very good. Now we like to see the future. So where do you think we're going to be in the data center fabrics, like let's say next year or 2 years down the road? Where you see ourselves on this, or Cisco or yourself? Where you think if you have a crystal ball, where you think you?
I think it's a hard question. So I think there's a lot of activity happening, and we're I think bringing a lot of new innovations to this space. I think I'm very excited about what we're going to see in the next year or two, but it's all kind of under works.
That's excellent. I'm sure he cannot talk about it on the NDA. Sorry, but this has been great. This has given a lot of insight on why you guys have decided to put the merchant plus strategy versus just stick with just the merchant only strategy. You decided to use the spine just the merchant only because you want to keep that. You want to keep the cost. So, Chad, you want to add anything else before I close it? Any other?
No, just thanks, Mohammed, for your time and participation in this. And I think this gives a lot of network architects a great deal of knowledge on how spine leaf architecture should be designed, what are the considerations that to look at, and what are the outputs or the consequences if you don't design or use the right buffers, link speeds, and whatnot within the data center fabric. So we appreciate your time going through this. Look forward to the next discussion to dig deeper into those different performance key features of ACI and Nexus 9K.
Thanks a lot for having me. I also look forward to our next discussion.
Yeah, this has been great, and hopefully everybody enjoys it. And if you have any questions, please let us know. Thank you very much. Appreciate your time.